So begins lecture 20 on sums of squares and the Gaussian integers. So let's get to it. What are Gaussian integers? Well, Gaussian integers are integer linear combinations of just regular integers and the imaginary number I. So things of the form a plus bi, where a and b are themselves integers. So it's a subset of complex numbers. And it turns out that these are very useful to analyze certain questions in number theory. The nice thing about this particular set is that since it's a subset of the complex numbers, we already know how to add, subtract, multiply, divide, take the complex conjugate, lots of things. So for the purpose of this, in the next lecture, we're going to define the norm on the Gaussian integers to be this big N. So what N does is it takes in a Gaussian integer and it outputs a non-negative integer. And the way we define the norm is just to take the sum of the squares of the components like that, right? Of course, we know we could also write the norm of z as zz bar. That would give us the same formula, right? And so I decided to leave you a nice homework on this. So probably one of your first homeworks will be to prove that the norm satisfies these properties. In particular, the norm of z times w is the norm of z times the norm of w. The norm of z is positive or 0. That's pretty much immediate from this formula right here, right? And then also the norm of 0 is equal to 0. Excuse me, the norm of z is equal to 0 if and only if z is in fact equal to 0. Let's see here, what else should I tell you about? Well, z in the integer, Gaussian integer is a unit if there exists a w in the Gaussian integer such that z times w is equal to 1. For example, same definition in the integers, right? A unit in the integer is an integer such that z times w equals to 1 for some other integer w. So for the integers, the only units are plus or minus 1. All right. The only numbers you can get to multiply to 1 in the integers are just 1 and minus 1. Right. 2 is not a unit in the integers because 1/2 is not an integer. Now, that said, the units in the Gaussian integers there's a little bit more to them. There's actually 4 of them as it happens, and here's what they are. So the only units in the Gaussian integers are 1, minus 1i, and minus I. So you got these four units, right? Of course, this is the 4th roots of unity, right? So the units of the Gaussian integers are the 4th roots of unity. Here's the proof. If you have z times w is equal to 1, then if we take the norm of that equation, then we get norm of z, w is norm of z, norm of w, thanks to your homework. Which gives me norm of 1, which is 1, all right, because 1 squared plus 0 squared is 1. And so what do we get? This is the product of two numbers being equal to 1, but since these are positive, right, they can't be 0 because we can't have 0 times something equal to 1. So they're both positive, and then that forces them to both be 1. All right, so we get the norm of a plus ib, which is a squared plus b squared equal to 1. And if you just sort through it, the only way you can get any solution to this is either a equals to plus or minus 1 and b equals to 0, or a equals to 0 and b equals to plus or minus 1. And those 4 choices respectively correspond to 1, minus 1, I, and minus I. And there you have it. There's your units. We'll see that this the fact that there's 4 units means that we often have 4 choices as we go on. In a similar vein, if you think about number theory over the natural numbers versus number theory over the integers, if you work over integers, sometimes you have 2 choices because you've got plus and minus because you got 2 units, whereas with the Gaussian integers, it turns out we have 4 choices because we've got 4 units. I'll show you what I mean as we go on here by that somewhat fuzzy comment. Many things are possible in the Gaussian integers just as they were in the integers. First of all, there is a division algorithm. Let me kind of sketch out how that works. It's a little bit different, but it's also not so different. So here's the way it goes. What you do is if you want to find, so you got a is 10 plus 3i and b is 2 plus 3i. These are Gaussian integers, right? And we want to find, the remainder of a divided by b. So what I do is I calculate a over b as a complex number. I multiply by the conjugate or the conjugate as usual to rationalize it, And that gives me 29 over 13 minus 24i over 13. Then what you want to do is you want to pick a complex number which is as close to this as you can get. Now 29 over 13 is close to 26 over 13, which is 2. And 24 is close to minus 26, which is minus 26 over 13 is minus 2i. So you see this number 2 minus 2i, that's kind of close to AB, all right? And so what I mean by close is both the real and the imaginary components have to be either a half a unit or less, all right? And that's always possible to find a complex number that's no more than a half a unit away there. Anyway, so here we go. So I put my q, my quotient, 2 minus 2i. So q times b is 10 plus 2i. If I subtract qb off a, that gives me I. I call that the remainder. All right? And so there you have it. We found a quotient and a remainder in Gaussian integers such that a is equal to qb plus r, and the norm of r, in this case, is equal to 1, and that's less than 13, which is the norm of b. And so that sort of frames it for you. Here's the division algorithm for the Gaussian integers. Given a and b Gaussian integers with b non-zero, well, there exists a quotient and remainder Gaussian integer with a equals to qb plus r, and either r is 0, or that norm of r is less than the norm of b. I guess you could just say norm of r less than or equal to b. Well, norm of r less than b, I should say. Less than norm of b. But, so, yeah, and like example 1 illustrates how that division algorithm is accomplished. Don't worry, I have more examples. So let's see here. A little bit more definitions while we're at it. So we say z divides w in the Gaussian integers if there exists a c such that w is equal to cz. Also, for z and w Gaussian integers, if z divides w, then we say w is a multiple of z. All right. If z is a Gaussian integer and w divides z, implies w equals to z, or w is an element of the units, then that means z is prime. Equivalently, we could say z is prime if whenever you factor it, the norm of one of the factors is 1. In other words, any factorization of the prime has to force one of the factors to be a unit. Again, a third equivalent statement to the two I've written there. Well, that's the same. That's what I wrote there. Let me shut up. So this is a prime in zi, but we're just going to keep calling it a Gaussian prime. Okay. So, for example, 1 plus I has the norm of z is 1 squared plus 1 squared, which is 2. And if you think about a factoring, all right, 2 is equal to z1, rather not 2, excuse me, 2, listen to me. If you think about a factoring of 1 plus I into z1 times z2, then we'd have 2 is equal to the norm of z1 times the norm of z2, all right? Which would then imply that either the norm of z1 was 1 and the other one was 2, or the norm of z2 was 1 and the norm of z1 was 2. So any way you slice it, if we've got the multiple of two numbers, right, both of them being integers, being 2, it forces this to either be 2 times 1 or 1 times 2. So, hey, great, that means that 1 plus I is in fact a Gaussian prime. See, you can write this Gaussian prime as the product of other Gaussian primes. For example, 1 plus I is 1 times 1 plus I. Well, it's kind of silly, but true. It's minus 1 times minus 1 minus I. Slightly less silly, but still true. It's also equal to I times I minus 1. Multiply that out, you get minus 1 minus I. Uno momento. Oh. Uh-oh. I do not buy that. Yeah, let's put a minus right about here to make that true. All right. And I need a minus here and a plus there to make it interesting. All right. Anyway, these are ways we could factor 1 plus I into a product of Gaussian numbers, but Gaussian integers rather. But in each one of the factors is a unit. All right. And this is a name. All right. If there exists a unit such that z equals to u times w, then z and w are called associates. All right. So the associates of 1 plus I, for example, are 1 plus I, minus 1, minus I minus 1, and I think I should have minus 1 plus I there, actually. If I didn't make a mistake. Anyway, so every Gaussian number, Gaussian integer rather, has 4 associates. All right. So, yeah. Moving along here. All right. So here's another example. So one of the main goals of this lecture is to just gain some, at least beginning intuition about what is a Gaussian prime and what's not. It's a little bit surprising sometimes what the story is here. And then hopefully by the next lecture we'll apply even this lecture we'll apply the Gaussian numbers to begin to solve some interesting questions. Although I do think they're interesting for their own right, even independent of their application. Anyway, so here it is. 2 is actually not a Gaussian prime because we can factor 2 as 1 plus I times 1 minus I. And now 1 plus I and 1 minus I, those are separately Gaussian primes, right? They have norm 2. So the number 2 permits a factorization inside the Gaussian integers, which has non-trivial unit factors. So 2 is not a Gaussian prime, even though 2 is a regular prime, right? 2 is a prime in the integers, but it's not a prime in the Gaussian integers. On the other hand, 3 is a prime in the integers, and it's also a Gaussian prime. And it takes a little bit of work to prove it, so that if 3 is equal to z1 times z2, well, the norm of 3 would be 9, because 3 squared plus 0 squared is 9. Now, if 9 is equal to the product of the norm of z1 and the norm of z2, then factoring 9 either gives us 1 times 9, 3 times 3, or 9 times 1. Now 1 times 9 and 9 times 1 is not a problem because that means that we're looking at unit factorizations which contain at least one unit. But 3 times 3, that would be a problem. That would be a problem. We need to disprove 3 times 3 as an option. In other words, we need to explain why it is that it's not possible to have a plus ib equal to 3. The norm of a plus ib equals to 3. So we'd have to solve a squared plus b squared equals to 3. And if you sort through that, it just isn't possible. Just look at look at the plausible numbers, right? 1 squared plus 1 squared is 2, 1 squared plus 2 squared is 5, 2 squared plus 1 squared is 5, 2 squared plus 2 squared is 8, 2 squared plus 0 squared is 4, and it only gets worse from before or after that, you know? So it's impossible to get 3 as the sum of 2 squares. Now, so 3, therefore, if you factor it, has to have either norm of z1 or norm of z2 being 1. Therefore, 3 is a Gaussian prime. Now, I think we proved things about sums of squares earlier, and I'm sorry, I should have taken a little bit of time to look those up. So my memory is not what it used to be. I can't remember everything we've done in this course, unfortunately. But I do think that if I was a little bit more with it, I could probably leverage some things that we've done previously to say things about some of the things I have to say about sums of squares in this lecture. So anyway, my apology. I would definitely lose memory to my kids every time. So here we go. Hey, but I am going to remember to do this. The secret word for today is the ace of spades. There you go. All right. Now, so you start to see in the last two examples the fact that divisibility in the Gaussian integers is tied to the corresponding divisibility of norms of Gaussian integers. Here's a theorem. If you have Gaussian integers alpha and beta, and alpha divides beta, then the norm of alpha divides the norm of beta. Here's the proof. So if we have alpha divides beta, that means beta is equal to C alpha, which means the norm of beta is the norm of C times alpha, which is the norm of C times the norm of alpha. But that shows that the norm of alpha divides the norm of beta. So, hooray! Hey, there's a nice test question right there, isn't it? Just saying. All right. Threats aside, let's look at what this whole business has to say about sums of squares. So here I'm introducing some notation that I got from Jones and Jones, number theory, and I'm not really following Jones and Jones here precisely. I'm not really following any specific book precisely. I'm putting together a couple different things. Anyway, I won't blame any of them. It's mostly my fault. So here, for k in the natural numbers, we define s sub k as to be numbers which are formed from the sum of k squares, where the numbers we're picking are integers. All right. So for example, s1, it would just be the set of squares, right? s2 would be 0, 1, 2, 4, 5, 8, and so forth. Zero's in there because 0 squared plus 0 squared is 0. 1's in there because 0 squared plus 1 squared is 1. 2's in there because 1 squared plus 1 squared is 2. 4's in there because 0 squared plus 2 squared is 4. 5's in there because 1 squared plus 2 squared is 5. 8's in there because 2 squared plus 2 squared is 8. What's less obvious is why 3 is not in there, and why 6 is not in there, and why 7's not in there. But you can sort it out that there does not exist a pair of integers that the sum of the squares is equal to 3, 6, or 7. And of course, an interesting question to ask is, oh, okay, well, what exactly is S2 then? And well, perhaps we'll answer that by the end of next lecture. But we can say some things already. For example, we can say that S2 is closed under multiplication. In other words, if I take two numbers that are formed from the sum of squares, then their product is also a sum of squares. This was known to the ancient Greek mathematician Diophantus. It also was known to like Brahmagupta and the other Indian mathematician, whose name I can't pronounce. So these formulas are old, but the way I'm going to look at them is not the way those ancients looked at it. I'm going to look at it in terms of Gaussian integers. And so here it is. If we have a and b in S2, that means that there exists a1, a2, b1, b2 such that a is equal to a1 squared plus a2 squared, and b is equal to b1 squared plus b2 squared. Now, that means that we can write norm of a1 plus ia2 as a1 squared plus a2 squared, which is a, and the norm of b1 plus ib2 as b1 squared plus b2 squared, which is b. Right? So this step, this observe step, this is a sneaky, sneaky step. Right here, this is a very sneaky step, okay? But making that step allows us to leverage the property, the multiplicative property of the norm, to let it do the heavy lifting for us here. So AB is norm of this times norm of that, which is the norm of the product, and then multiply these numbers in the complex numbers to get a1b1 minus a2b2 plus I times a1b2 plus a2b1. That's just multiplying these two numbers. And then the norm, by definition, gives us the square of the real part plus the square of the imaginary part. So apparently, a times b is the sum of squares, which means it's in S2. So there you go. It's kind of neat. Here, let's kind of use the method of the proof here to the theorem to actually create some examples, to extend my list for example 6, all right? So 5 is the norm of 1 plus 2i, and 8 is the norm of 2 plus 2i. right? So 40, which is 5 times 8, is the norm of that times that, which is the norm of... I seem to have lost a parentheses. I was just fussing at my own children for not doing this earlier, so I better fix it before they find out. Anyway, you multiply those two numbers, you get minus 2 plus 6i, which is 2 squared plus 6 squared. So yeah, of course, 40 is 4 plus 36, right? But notice that we've just derived it from multiplication of the Gaussian integers. That's kind of neat. And it gets neater when you go to bigger examples, right? So like here, 200 is 5 times 40. So I could do 1 plus 2i times 2 plus 6i, which would give me minus 10 plus 10i when you multiply it out. The norm of that gives me 10 squared plus 10 squared. So that's one way to write 200 as the sum of squares. But we could also, instead of doing... so notice that I changed the minus 2 to 2. That doesn't change the norm, right? And let's see here. If I do... let's see here. Minus 2... Okay, over down here. Norm of 1 plus 2i times the norm of minus 2 plus 6i. So instead of doing the plus 2, I did the minus 2 like I had before, okay? I'm still going to get the, product of 5 times 40, which is 200. But this time when I multiply those numbers out, I don't get minus 10 plus 10i, I get minus 14 plus 2i, which uncovers the fact that 200 is also 14 squared plus 2 squared. 14 squared is 196. So yeah, of course, 196 plus 4 is 200, right? So yeah, by the way a number is the sum of two squares need not be unique, right? And we're going to see that looking at how the sums of squares of numbers is connected to the underlying Gaussian integers will allow us to write sums of squares in many different forms if we understand the underlying Gaussian content. Anyway, so some further comments here. This is from page 201 of Jones and Jones. They have a little section on S3, sums of squares of three numbers, and that's a little bit harder. In particular, it's not closed under multiplication. So like S3 is not anything too nice. This was known to Gauss, right? On the other hand, surprisingly, perhaps, S4, sums of squares of four numbers, up to four numbers, actually gives you every natural number. Every natural number is the sum of at most four squares. This theorem is due to Lagrange in 1770. It's known as the four squares theorem. And the four squares theorem, the complete proof of it, in some sense rests on the structure of what are known as quaternions, something we'll talk about in a future lecture. So quaternions give you a nice proof of the closure of S4 under multiplication, in the same sense that Gaussian integers just showed you on this page that S2 is closed under multiplication. All right. So anyway, there's that. Another example. Example 9. So, and don't worry, we're going to circle back to the division algorithm stuff at the end of this lecture. I've got more of them to come. Here we go. 4 plus I is a Gaussian prime. Why? Well, if z is alpha beta, then the norm of z, which is 17, is equal to the norm of alpha times the norm of beta, which means that either the norm of alpha is 1, or the norm of beta is 1. See, because the only way to factor 17 with positive numbers is 1 times 17 or 17 times 1. So there you have it. It's a Gaussian prime. All right, theorem. If z is a plus bi with b not equal to 0, and that has the norm of z is a squared plus b squared equals to p a prime, then z equals a plus ib is a Gaussian prime. Moreover, a minus ib equals z bar, right, is also a Gaussian prime. Let's see why. So here's the proof. Suppose n is equal to a squared plus b squared, which is equal to p, and that's a prime. All right. Then suppose that alpha beta is a factorization of a plus ib. Well, then the norm of z would be equal to p, right? Which is equal to the norm of alpha times the norm of beta. Now that would mean either norm of alpha is 1 or norm of beta is 1, because again p was assumed to be prime, right? So therefore a plus ib is a Gaussian prime. In other words, this theorem is just doing example 9 in the abstract. Okay, it's really nothing more than that at the start of it. So the next bit is a little bit more interesting, perhaps. If we look at z conjugate, a minus ib, and suppose the z conjugate has factorization lambda delta, then z bar bar is z, because the conjugate of the conjugate is the thing again. But z bar is also equal to lambda delta bar, which is, remember, the conjugate of the product is the product of the conjugates, so that's lambda bar delta bar. And that tells me that the norm, since remember we're assuming that we already proved that z was a Gaussian prime, so that means that the norm of lambda bar is 1 or the norm of delta bar is 1. But on the other hand, we can also prove that the norm of lambda bar, which by definition is lambda bar bar, which is lambda bar lambda, which is norm of lambda. And likewise, the norm of delta bar is the norm of delta. So what did we get? Well, we got that the norm of either lambda or delta was 1, which is to say that z bar is also a Gaussian prime. So that's kind of nice. Now, so let's see here. An example. Example 10. We have z equals 5 plus 2i. That has norm of z is 25 plus 4, which is 29. That's prime, pretty sure. Therefore, z plus or minus 2i, these are Gaussian primes. So, that's nice. So it's a nice way to come up with Gaussian primes, right? If the norm of the number is a prime, then it's prime. Now those aren't the only ones. There are also Gaussian primes which are ordinary primes, like we saw, right? 3, for example, is a prime which is also a Gaussian prime. So, but again, not every real prime is a Gaussian prime. So there's something to unravel there, isn't there? All right. Here's another step in that direction. If p is a natural number and it's a prime, then p is a Gaussian prime if and only if, all right, there does not exist a and b in the integers for which p is equal to a squared plus b squared. All right. Okay, let's sort through this here. So converse direction. Suppose there does not exist a and b such that p is equal to a squared plus b squared. All right. Now let's suppose that you could factor that p, right? And this p we're assuming is a prime in the integers, right? So p is a real integer. And we're supposing it's got somehow a complex factorization, gamma 1, gamma 2. Well, since p is equal to p bar, that means that p squared is p times p bar, which we can write as gamma 1, gamma 2, gamma 1, gamma 2 bar. Which then properties of conjugates give me gamma 1, gamma 2 bar times gamma 2, gamma bar, which is the product of x1 plus x2 squared times y1 squared plus y2 squared, I should say. So you've got a prime squared is equal to a product of these two natural numbers, right? So there are 3 choices. Either the first product is prime squared, and the second one's 1. The first one's 1, the second one's whoa, they can't both be 1. No. Rats. I've misplaced my brown marker, so we'll have to do gray here for the moment. P squared, right? Yeah, that's better. Okay, duh. So this one's 1, that one's p squared, this one's p, this one's p. So it's either p squared and 1, or 1 and p squared, or p and p. Those are the possible factorizations of p squared into a product of 2 things, right? So consequently, as we cannot have option what? We cannot have option 3 because we can't have that the prime is the sum of squares, right? That's what we assume that wasn't the case. So we're forced to do options 1 or 2, right? And at least one of the gamma 1 or the gamma 2 is a unit, right? And so what does that mean? Oh, that means that P is a Gaussian prime, doesn't it? Right? Because we tried to factor it in the Gaussians, and we were forced to say that either one or the other of the factors was a unit. So therefore P is a Gaussian prime. Okay? Now the converse direction. If we assume P is a Gaussian prime, and P is equal to a squared plus b squared, right, towards a contradiction, because we're trying to show it's not the case, right? Then if it was equal to a squared plus b squared, then we could factor a plus ib times a minus ib, where the norm of a plus or minus ib is p, which would be bad because that would be a non-unit factorization of the prime, which we cannot have. I mean, I would say P is not a Gaussian prime, but we're assuming it is a Gaussian prime, which of course is a contradiction. So there you go. That's the theorem, if and only if. Now, all right, so as we've seen and now proved, some primes in the natural numbers are also primes in the Gaussian integers, but some are not. How to classify all primes in the Gaussian integers? Well, we'll return to this in lecture 21. Now let's see what else in the integers generalizes to the Gaussian integers in terms of arithmetic. So here we go. Arithmetic in the Gaussian integers. So first of all, there is a fundamental theorem of arithmetic. Any Gaussian integer factors into a product of Gaussian primes, and this product is unique up to choice of associates. That's pretty cool. I'm not going to prove it, but the proof is similar to the one which was given for integers. And so here's an example, just putting it into practice. If you're wondering how I factored 5 plus 31i, the answer is simple. I started with these and I multiplied them out and I got that. So actually factoring Gaussian integers is it's a pain. So anyway, here it is true that this is equal to this times that. And I wanted to emphasize what I mean by up to choice of associates. See, I can multiply this one and that one by -1, and this is another way to write that product, right? Or I could multiply this one by I and this one by -i, and that gives me this times that. Or I could leave the first one alone and multiply the second one by -i and the last one by I respective. So basically I'm just shoving in factors of 1, where 1 is either -1 times -1 or it's -i times I. And so yeah, the Gaussian, the factorization into Gaussian primes, it's not unique, but it is close to unique. We just have this issue of multiplication by the units to contend with. The same was true over the integers. We just don't really appreciate it much, right? Somebody says, how would you factor, 22? But you're like, well, it's 1 times 22, right? Or it's 2 times 11. And most people would be like, oh, okay. But the thing is, and this matters actually to factoring, is there are also factorizations of -2 times -11, right? Or -1 times -22. All of those things matter to factoring, don't they? But anyway, it's just since we have 4 units, we got 4 choices, like I was saying earlier in this lecture. Now, camera just looked a little fuzzy. I hope that was just my eyes. I did set the zoom length, so it shouldn't be fuzzing. Anyway, all right, example 12. By the way, these are Gaussian primes. I know that from, we did those earlier in example 2, 9, and 10. 12. How does 12 factor over the Gaussian integers? Well, 12 is 4 times 3, which is 2 squared times 3. But 2 is not a Gaussian prime, but it does factor into a product of Gaussian primes, 1 plus I times 1 minus I. Square in both of those, because I got 2 squared, I get 1 plus I squared, 1 minus I squared times 3. So there's the Gaussian factorization into primes. 45 plus 18i. I can factor a 9 out. 5 plus 2i is a Gaussian prime, as we were just talking about. And 9 is 3 squared. That's the prime squared. So there's the prime factorization of 45 plus 18i. All right. So, yeah. What else can we do? We can define the GCD. And I shouldn't really say define the GCD. I should say we can define a GCD. There will be 4 of them. All right? Because there's always a choice of multiplying by one of our 4 units. But we'll say D is a GCD of A and B if D divides A and D divides B. In other words, D is a common divisor, and the norm of D is smallest possible. In other words, if D tilde divides A and D tilde divides B, then the norm of D tilde is greater than or equal to the norm of D. Right? So if you think about this, if we have D that is the GCD, then if we can look at plus or minus D and plus or minus ID, and they'll all be reasonable choices for GCD of AB. All right. The vector Euclidean algorithm still applies to Gaussian integers. There's a Bezout's theorem, right? If you have Z and W not both 0, there exist A and B, such that AZ plus BW is equal to GCD ZW. And there's also a Euclid's, I forget what this is, maybe this is Euclid's lemma, but this property that if you have a prime that divides a product, then it divides either the first factor or the second factor in the product. So we still have this theorem about primes and divisibility. All right. And the proofs of both of those are similar to the proofs we gave before. Actually, the proof of Bezout's theorem is essentially because, hey, there's the vector Euclidean algorithm, and it allows you to find the coefficients, the Bezout coefficients, which I'll illustrate with examples here shortly. Example 14, we have 11 plus 3i and 1 minus i. We're dividing. I'm trying to illustrate the division algorithm, so I do that. And we get 8 plus 14i over 2, which is 4 plus 7i. Oh, hey, z over w is actually a Gaussian integer. Well, this is embarrassing. The remainder in this case is 0. So in this case, w divides z, so the GCW of z and w is just w. So there you go, that's example 14. Example 15, perhaps a little bit more exciting. We have this time 11 plus 3i and 3i plus 2. All right. So let's walk through it here. Let me scooch this up a bit. So I'll start by dividing z by w, and then I make it, multiply the conjugate over the conjugate denominator to make it in the Cartesian form. 13 minus 27i over 13, 31 rather. And so that's approximately like 26 over 13 minus 26 over 13 times I, which is 2 minus 2i. So my first quotient, q1, is 2 minus 2i. Now, when I multiply q1 times w, I get 10 plus 2i. Then my r1 is going to be z minus q1w. That's the first remainder, which works out to 1 plus I here. Notice that the norm of the remainder 1 is 2, whereas the norm of w was that 13 there. All right. So of course 2 is less than 13. That's a good sign. Now, so we have z is q1w plus r1, like that. 1 plus I is a Gaussian prime. That's nice, but kind of irrelevant. This sentence right here, whatever. Next, moving on, w divided by r1. Right. The next thing we do is we divide the dividing number by the first remainder, and so I'm going to use the usual approach we did here. And what happens? Well, we've got 5 plus I over 2, which is, if it's close to a real number, then use a real number, it's easier. This is approximately 2, because this is 2.5 plus 0.5 times I, so it's close to 2. So then I take w minus r1 q2, which in this case gives me back I. Once you get the remainder is a unit, that means the next step would take you to 0. We don't ever care about that last step. At least I don't. And so the GCD of 11 plus 3i and 3i plus 2 is in fact equal to I. And here is the, down here, here's the vector Euclidean algorithm, where I'm just going through the steps above, like in the usual kind of notation. Although it's unusual, I guess, because we haven't done this before. But so 11 plus 3i and 3i plus 2 is ZW. Then I put the 3i plus 2 down there, which brings this w down here. And then the remainder was 1 plus I. How did I get 1 plus I? That was R1. I did z minus q1w. Z minus q1. Well, q1 was 2 minus 2i, so there it is, z minus 2 minus 2iw. Then we bring the first remainder down to here, and so that brings this down to there. And how do I get that? How do I get this I, right? That comes from w. That's the second remainder, right? So the second remainder is I, and that comes from w minus r1 q2. So that is w minus r1 q2, which is, the q2 is the 2, I believe, yeah, and the r1 is this stuff here. So it's the usual pattern, guys. Don't get lost in my words. It's just the usual pattern. And so put that all together, we get minus 2z plus 4 minus 5. 5 minus 4i times w is equal to I. So this is Bezout's theorem in practice here. One more example. So here we have z is minus 4 plus 2i, and w is 3 plus 2i. I want to calculate the GCD of these guys. So I'm going to illustrate division, and a successive division where I'm doing the Euclidean algorithm, right? So z over w, it works out to minus 18 plus 4i over 13, which is close to minus 1 plus I. q1, that's my q1. So then r1 is z minus q1w, which works out to 1 plus I. All right, great. And then I do w divided by r1, which works out to 5 minus I over 2. Again, my second quotient is about 2, so why not use the 2? R2 minus Q2 R1 is 3 plus 2i minus 2 times 1 plus I, which is 1. So the GCD of these two is 1 again. All right, I'll probably give you one in the homework where the GCD is not 1, it's something else. So this is the one. The homework will be a little bit different than these because it won't, the last non-zero remainder won't be a unit, Okay, so anyway, here's the calculation that I just did above, guides the vector Euclidean below, right? Now, when I'm doing the ordinary vector Euclidean algorithm, I can kind of just do it in the vector way to start with, but I'm finding that I kind of need to think through it before I try to do the vector thing. I don't know, you find the notation which is best for you, but here's just to sort it through it here. We had minus 4 plus 2i and 3 plus 2i were z and w. We bring the w down, 3 plus 2i, and then the remainder of the previous division was 1 plus I, so that's my first remainder, right? That came from subtracting minus 1 plus I times w off z, all right? And then when we divide this into that, our remainder was 1, right? And that came from taking w and subtracting twice the first remainder, which, by the way, was z plus 1 minus I times w. I distributed the minus through there, right? And there you have it. 1 is equal to that, which means that 1 is equal to minus 2z, and then I just clean things up here because I've got a 1 minus, oh man, did I mess that up? Really? Well, the minus 2z seems right. But this would give me w and then minus 2w. I think that 2 there should just be a 1. And then I think I forgot to distribute the 2. And then minus 2 times minus I gives me what? Plus 2i, right? So 2 plus 2i. So this should be 1 plus 2i, unless I've made yet another mistake. Hopefully not. All right. Because w subtract 2 from 1 gives me minus 1. What did I say? Subtract 2 from 1 gives me, not 1 gives me minus 1, dummy. Minus 1. Minus 1. And then minus 2 times I gives me plus 2i. Good. All times w, right? The minus 2z, I don't think I messed that up. Okay, so anyway, it is the same pattern as before. It's just now we have to think in terms of the Gaussian integers. And yeah, these Gaussian integers are relatively prime because their GCD is a unit. All right, so anyway, that's it for this one. We will continue these thoughts in the next lecture. Thanks, guys.